September 15, 1940, RAF Biggin Hill, Kent, England. 1420 hours. Flight Lieutenant James McLeod pulled his Spitfire into a sharp climbing turn, the Merlin engine screaming as German Messerschmitts tore through the formation above him. He needed altitude. He needed speed. He needed to get behind that lead 109 before it could line up on his wingman. McLeod hauled back on the stick, forcing the aircraft into a tighter arc, feeling the G-forces multiply against his chest, his legs, his arms. The horizon tilted violently. His vision narrowed to a gray tunnel, then nothing. The Spitfire rolled inverted and fell, tumbling through 3,000 feet of empty sky while its pilot sat unconscious in the cockpit, eyes open, body pressed against the harness by forces his brain could no longer interpret. McLeod woke at 1,500 feet, vision clearing just in time to see the patchwork fields of Kent rushing upward. He leveled out, hands shaking, gulping oxygen through the rubber mask. Above him, the dogfight continued without him. Below, the English countryside waited, indifferent. He would survive the day. 73 other pilots would not. Across the Atlantic, in a cramped laboratory on the 4th floor of Toronto's Banting Institute, Dr. Wilbur Franks stood over a steel centrifuge, watching a white mouse rotate at increasing speed inside a clear chamber. The mouse weighed 28 grams. The centrifuge was spinning at 400 revolutions per minute, subjecting the animal to forces equivalent to 9 times Earth's gravity. Franks adjusted his glasses and checked the stopwatch. 30 seconds. The mouse remained conscious, pink feet gripping the mesh floor, whiskers twitching. At the same rotational speed 2 weeks earlier, an unprotected mouse had lost consciousness in 8 seconds. The difference was the liquid. Franks had immersed this mouse in a sealed chamber filled with saline solution, surrounding its entire body in incompressible fluid. The water distributed the G-forces evenly across every surface of the animal's body, preventing blood from pooling in its lower extremities, keeping circulation stable even as physics tried to drain its brain of oxygen. It was an elegant solution to a problem that was killing men in the skies over Europe every single day, and almost no one believed it would work on humans. Frank stopped the centrifuge and carefully extracted the mouse. It blinked at him, alive, alert, seemingly unbothered by an experience that should have rendered it unconscious or dead. He placed it gently in a recovery cage and made a note in his logbook. Test 47. Successful. He sat down at the wooden desk, pulled out a sheet of paper, and began drafting another letter to the Royal Canadian Air Force. The first letter had been polite. The second had included diagrams. The third had contained photographs of the centrifuge, the mice, the data tables showing survival rates at sustained high G exposure. None had received more than a brief acknowledgement. The RCF had more pressing concerns in September 1940. Britain was fighting for survival. Canada was mobilizing every resource it possessed to send aircraft, ships, and men across the Atlantic. A young researcher proposing to dress pilots in water-filled rubber suits was not a priority, but Wilbur Franks was not a man easily discouraged. Born in Weston, Ontario in 1901, he had studied medicine at the University of Toronto, specializing in the mechanics of human physiology under stress. He understood how the body responded to extreme environments, how circulation adapted to pressure changes, how consciousness depended on a steady supply of oxygenated blood to the brain. He also understood that modern warfare was pushing pilots into conditions the human body had never evolved to survive. Aircraft were faster, more maneuverable, and more deadly than anything that had existed 5 years earlier. Pilots pulled tighter turns, executed sharper dives, endured greater accelerations, and they were dying because their circulatory systems could not keep pace with their machines. The problem was simple physics. When a pilot pulled a tight turn, centrifugal force pushed blood away from the brain and toward the lower body. At 3 Gs, vision began to narrow. At 4 Gs, tunnel vision became severe. At 5 Gs, most pilots blacked out completely, losing consciousness for seconds or minutes, while their aircraft continued on whatever trajectory momentum dictated. Some recovered in time to regain control. Many did not. The official term was G-induced loss of consciousness, or GLOC. The pilots called it graying out, or worse, and they lived in constant fear of it. Franks had read the incident reports. He had studied the physiology textbooks. He had consulted with engineers at the National Research Council, with physicians at the military hospitals, with anyone who would listen. The consensus was grim. The human body had limits. Pilots would simply have to accept them. They could be trained to tense their leg muscles during high-G maneuvers, forcing blood back toward the heart and brain. They could wear tight belts around their abdomen. They could learn to grunt and strain, buying themselves an extra second of consciousness. But these were marginal improvements. The real solution, everyone agreed, would require changing the aircraft, not the pilot. Franks disagreed. He believed the pilot could be protected, could be given the tools to match the machine's capabilities. The answer lay in pressure, in surrounding the body with something that would resist the redistribution of blood, that would keep circulation stable even as G-forces tried to tear it apart. Water was the perfect medium, incompressible, evenly distributed, dense enough to counteract the forces, light enough to be practical. The challenge was designing a suit that could contain the water, seal it against the body, and allow the pilot to move freely enough to operate the aircraft. He began with rubber, sheets of vulcanized rubber sewn and glued into a crude prototype that covered the legs and lower abdomen. He filled it with water, sealed the edges, and tested it on himself, lying on a tilting table in the laboratory, elevating his feet above his head to simulate the blood-pooling effect of G-forces. The suit worked, to a point. It resisted the flow of blood, kept his vision clear longer than it should have. But it was clumsy, heavy, prone to leaks. It needed refinement. He spent the autumn of 1940 refining. He tested different rubber thicknesses, different sealing methods, different configurations. He recruited volunteers from the university's medical school, young men willing to lie on the tilt table for hours while Franks adjusted straps and valves and pressure gauges. He measured blood pressure, heart rate, oxygen saturation. He graphed the data, calculated the thresholds, identified the optimal pressure levels. Slowly, the prototype improved. It became lighter, more flexible, more reliable. It began to look less like a laboratory curiosity and more like something a pilot might actually wear. In November, Franks received a letter from Wing Commander Wilfred Curtis, Director of Air Research for the RCF. Curtis had seen the photographs of the mice. He had read the physiological explanations. He was skeptical, but he was also desperate. Pilot losses were unsustainable. If there was even a chance that Franks's idea could reduce G-lock incidents, it was worth investigating. Curtis arranged for Franks to demonstrate the suit at the RCAF testing facility in Downsview, just outside Toronto. The date was set for late November. Franks would have one opportunity to prove his concept worked. He spent 3 weeks preparing. He refined the suit, eliminating every unnecessary ounce of weight, every potential point of failure. He practiced donning and removing it, timing himself, ensuring it could be put on quickly in the chaos of a military airfield. He rehearsed his presentation, anticipating every objection, every question. He knew he would be facing officers trained to doubt, men who had seen 100 inventors promise miracles and deliver nothing. He needed to be flawless. November 26, 1940, RCAF Station, Downsview, Ontario. 8:30 hours. The demonstration was scheduled for mid-morning. Franks arrived early, carrying the suit in a canvas duffel bag, accompanied by a graduate assistant and 2 wooden crates of equipment. The testing hangar was cold, unheated. The concrete floor slick with frost. A small group of officers stood near a centrifuge device, larger and more sophisticated than the one in Franks's laboratory, designed to simulate the G-forces experienced in modern combat aircraft. They watched him approach with expressions that ranged from curiosity to outright skepticism. Wing Commander Curtis stepped forward, hand extended. He was a lean man, mid-40s, with the weathered face of someone who had spent years in open cockpits. He shook Franks's hand firmly, then gestured toward the centrifuge. The rules were simple. Franks would be strapped into the rotating arm of the centrifuge while wearing his suit. The machine would accelerate gradually, increasing the G-load until Franks lost consciousness or called for the test to stop. A medical officer would monitor his vital signs throughout. If the suit provided any measurable improvement over baseline human tolerance, the RCAF would consider funding further development. Franks nodded. He had expected nothing less. He opened the duffel bag and removed the suit, laying it out on a nearby table. It looked strange, alien even, a garment that seemed to belong more to deep-sea diving than aerial combat. The legs and lower torso were encased in thick rubber with reinforced seams and a series of valves along the thighs. A network of tubes connected the suit to a small hand pump that would pressurize the water once it was filled. The officers circled the table, examining the construction, asking technical questions about sealing mechanisms and pressure limits. Franks answered each one calmly, methodically, his voice steady despite the adrenaline beginning to tighten his chest. He changed into the suit behind a canvas screen, assisted by his graduate student. The rubber was cold against his skin. The water, pre-warmed to body temperature, flowed into the bladders through the fill valves, surrounding his legs and abdomen in a firm, unyielding embrace. He tightened the straps, checked the seals, and stepped out from behind the screen. The officers stared. One of them, a squadron leader with a pilot's wings on his chest, shook his head slowly as if witnessing something absurd. Franks walked to the centrifuge. The medical officer attached electrodes to his chest, clipped a pulse oximeter to his finger, and fitted him with a tight-fitting helmet designed to prevent head movement during rotation. Franks was strapped into the seat, a 5-point harness pulling him firmly against the padded backrest. The centrifuge arm extended 12 feet from the central axis. At maximum speed, it would generate forces equivalent to those experienced in the tightest combat turns. The control panel operator looked to Wing Commander Curtis, who looked to Franks. Franks gave a thumbs up. The motor engaged with a low hum. The arm began to rotate slowly at first, the world outside the centrifuge starting to blur into streaks of gray and white. Franks felt his body press harder against the seat as the speed increased. 2 Gs, 3. The pressure in his legs intensified as blood tried to pool in his lower body, but the water-filled suit resisted, pushing back with equal force, keeping his circulation stable. 4 Gs. His vision remained clear. His breathing was labored but controlled. 5 Gs. The pressure was immense now, every muscle straining, but his vision showed no signs of the gray tunnel that should have been closing in. 6 Gs, the officers standing beside the control panel exchanged glances. At 6 Gs, an unprotected human should have been unconscious. Frank's pulse was elevated, his breathing rapid, but the monitors showed no signs of cerebral hypoxia. Curtis leaned closer to the readout screens, his skepticism beginning to crack. 7 Gs. Franks felt his consciousness waver for the first time, a brief flicker at the edge of his awareness, but it passed. The suit was holding. 8 Gs. His body felt like it weighed over 1,000 pounds, every breath an effort, but his mind remained lucid. He could still see, still think, still process what was happening. The centrifuge held at 8 Gs for 10 seconds, then 20, then 30. Curtis raised his hand, and the operator began the deceleration sequence. The centrifuge slowed gradually, the G-forces easing, Franks's body relaxing back into something resembling normalcy. When the arm finally stopped, the hangar was silent except for the fading whine of the motor. The medical officer unstrapped Franks, checked his pulse, his pupils, his blood pressure. Everything was within acceptable ranges. Franks stood, slightly unsteady but conscious, alert, and very much alive after an experience that should have rendered him incapacitated. Wing Commander Curtis stepped forward, staring at Franks as if seeing him for the first time. He asked one question. Could Franks build more of these suits? Could he build them for operational pilots in time to matter? Franks said yes, he could build them, he would build them, and they would change everything. But first they would need to prove it could work, not just in a laboratory, not just on a centrifuge, but in the air, in combat conditions, where lives hung in the balance and failure meant death. December 1940. Banting Institute, Toronto, Ontario. The funding arrived within a week. Not a generous budget, but enough. Enough for materials, enough for assistance, enough to transform a university research project into something resembling a military development program. Franks cleared an entire floor of the Banting Institute, requisitioned sewing machines from a textile factory in Hamilton, and hired 2 seamstresses who had previously worked in medical corset manufacturing. They understood how to work with rubber, how to create garments that needed to fit precisely, to seal completely. to withstand pressure without tearing. These skills, developed for supporting injured spines and weakened abdomens, would now be repurposed for keeping pilots conscious at the edge of human endurance. The first production challenge was scaling. The prototype suit had been custom-fitted to Franks himself, adjusted through dozens of iterations until it worked. Creating suits that would fit pilots of different heights, weights, and body types required developing a sizing system, creating patterns, establishing standardized construction methods. Franks worked with the seamstresses to translate his hand-sewn prototype into something reproducible. They drafted patterns on large sheets of paper, cut them from sheets of rubberized canvas, experimented with different stitching techniques and adhesive compounds. Every seam needed to be watertight, every valve needed to be reliable, every strap needed to hold under stress. By January 1941, they had produced 6 functional suits in 3 different sizes. Each one was tested on volunteers, adjusted, retested. The suits were uncomfortable. There was no avoiding that. They were heavy, restrictive, and required help to put on properly. But they worked. On the centrifuge at Downsview, test subjects wearing the suits consistently maintained consciousness at G levels that would have incapacitated unprotected individuals. The data was undeniable. The question now was whether the suits would work in actual flight, where G-forces were unpredictable, dynamic, and accompanied by the chaos of combat. Wing Commander Curtis arranged for flight testing at RCAF Station Trenton. On the northern shore of Lake Ontario, the test pilot would be Flight Lieutenant Fred Hibbard, a veteran instructor with over 2,000 hours in high-performance aircraft. Hibbard had the experience to push an aircraft to its limits while maintaining enough control to abort if something went wrong. He also had a reputation for skepticism toward new equipment, which Curtis considered an asset. If Hibbard endorsed the suit, others would listen. February 12, 1941, RCF Station Trenton, Ontario. 06:45 hours. The morning was brutally cold, the kind of cold that turns breath to ice and makes metal burn to touch. Franks arrived at the airfield before dawn, carrying 2 suits in reinforced canvas bags. Hibbard was already in the hangar, conducting his pre-flight inspection of a Hawker Hurricane, one of the frontline fighters being used to train Canadian pilots before they shipped overseas. The Hurricane was fast, maneuverable, and capable of generating the kind of sustained G-forces that made pilots black out in combat. It was the perfect test platform. Hibbard turned as Franks approached, his expression neutral. He was in his early 30s, compact and wiry, with the kind of calm intensity that came from years of flying aircraft that could kill you if you made a single mistake. Curtis had briefed him on the suit, shown him the centrifuge data, explained the theory. Hibbard had listened politely and reserved judgment. He would evaluate the suit the same way he evaluated every piece of equipment, by whether it helped him do his job or got in the way. Franks laid out the suit on a workbench, explaining each component: the leg and abdomen bladders, the fill valves, the hand pump for pressurization, the quick release mechanism in case of emergency. Hibbard examined everything carefully, asking practical questions: how long to put it on, how much mobility in the legs, what happens if a valve fails at altitude. Franks answered each question honestly. The suit added approximately 3 minutes to pre-flight preparation. Leg mobility was reduced but sufficient for operating rudder pedals. A valve failure would simply depressurize that section of the suit, reducing effectiveness but not creating a hazard. Hibbard nodded slowly, still unconvinced but willing to try. He changed into the suit in a side room off the hangar, assisted by Franks and a medical corpsman. The rubber was even colder than the ambient air, and Hibbard grimaced as the frigid water filled the bladders around his legs. Franks worked quickly, checking seals, tightening straps, ensuring everything was secure. When they finished, Hibbard stood and tested his range of motion, bending his knees, twisting at the waist. The suit was restrictive, but manageable. He walked toward the Hurricane, his gait slightly stiff, but functional. The ground crew helped him into the cockpit, a process made more complicated by the bulk of the suit. Once strapped in, Hibbard ran through his instrument checks, started the engine, and waited for the oil temperature to rise. Franks stood on the tarmac with Wing Commander Curtis and a small group of observers, watching as the Hurricane taxied to the runway. The plan was straightforward. Hibbard would climb to 10,000 feet, then execute a series of increasingly aggressive maneuvers, pulling progressively higher G-loads until he reached his tolerance limit or the suit's effectiveness ceiling, whichever came first. He would report his vision status and physical condition via radio throughout the test. A chase aircraft would follow at a distance, ready to intervene if anything went wrong. The Hurricane's engine roared to full power, and the aircraft accelerated down the runway, lifting off smoothly into the gray winter sky. Franks listened to the radio chatter as Hibbard climbed, his voice calm and professional, calling out altitudes and headings. At 10,000 feet, he leveled off and began the test sequence. The first maneuver was a standard level turn, 4 Gs sustained for 10 seconds. Hibbard's voice came through clearly. Vision normal, no gray out, suit pressure holding. The observers exchanged glances. 4 Gs should have produced at least some peripheral vision loss. Hibbard sounded completely unaffected. The second maneuver was a climbing turn, 5 Gs sustained for 15 seconds. Again, Hibbard reported clear vision, controlled breathing, no loss of awareness. Curtis leaned closer to the radio operator, watching the altimeter readout transmitted from the Hurricane. The aircraft was maintaining perfect control throughout maneuvers that should have been pushing Hibbard to the edge of consciousness. The third maneuver was an aggressive pull-up from a shallow dive, 6 Gs sustained for 20 seconds. This was the threshold where most pilots began to experience significant problems. The radio crackled. Hibbard's voice was strained now, breathing audible, but still coherent. Vision narrowing slightly at the edges. Still in control. Suit working as designed. Franks felt his chest tighten. 6 Gs for 20 seconds. In a combat scenario, that could be the difference between evading enemy fire and being shot down. Hibbard requested permission to push to 7 Gs. Curtis hesitated, then approved. This was beyond standard testing protocols, beyond what any pilot should be expected to endure for more than a few seconds. The Hurricane banked sharply, the engine howling as Hibbard hauled back on the stick, forcing the aircraft into a brutal ascending turn. 7 Gs. The radio was silent for 5 seconds. 10. 15. Then Hibbard's voice, tight with strain but still focused, still conscious, still flying. Vision tunneled, but present. Suit maintaining pressure. Backing off now. The Hurricane leveled out and Hibbard reported returning to base. The chase aircraft confirmed he was maintaining steady flight, control surfaces responding normally. Franks exhaled slowly, realizing he had been holding his breath. Curtis was smiling, a rare expression for the normally reserved officer. The ground crew prepared for landing, and 12 minutes later the Hurricane touched down smoothly, taxied back to the hangar, and shut down. Hibbard climbed out of the cockpit slowly, assisted by the ground crew. His flight suit was soaked with sweat beneath the rubber anti-G suit, his face flushed from exertion. He pulled off his helmet and leather flying cap, ran a hand through damp hair, and walked directly to where Franks was standing. For a moment he said nothing, just looked at Franks with an expression that was difficult to read. Then he extended his hand. "The suit works. It bloody well works. I should have been unconscious at 6 Gs. I pulled 7 and stayed aware enough to fly the aircraft. If we had these in operational squadrons right now, we would save lives. Lots of them." Curtis stepped forward, already thinking logistics. How many suits could Franks produce per month? How quickly could they be shipped overseas? What kind of training would pilots need to use them effectively? Franks answered as best he could. With expanded facilities and more seamstresses, perhaps 20 suits per month initially, scaling to 50 or more as production methods improved. Shipping could happen as soon as the suits were ready, though ideally they would want to conduct more flight testing first. Training would be minimal, mostly familiarization with donning the suit and operating the pressurization pump. But there was another challenge Franks did not mention immediately, one he had been wrestling with since the centrifuge tests at Downsview. The suits worked, but they were not perfect. They were heavy, uncomfortable, and required pre-flight preparation time that could be problematic in combat conditions where pilots needed to scramble quickly. More critically, the water-filled bladders were vulnerable to temperature extremes. In the frigid air at high altitude, the water could freeze, rendering the suit useless or even dangerous. Franks had been experimenting with anti-freeze compounds, but finding a solution that was safe, effective, and did not degrade the rubber was proving difficult. He explained these concerns to Curtis and Hibbard in the hangar after the flight. Both men listened carefully. Hibbard pointed out that most combat occurred at altitudes where freezing was less of an immediate concern, and that even an imperfect suit was better than no protection at all. Curtis agreed, but emphasized that any suit deployed operationally needed to be reliable across all conditions. He authorized continued development work with the goal of having a cold weather variant ready for testing within 2 months. Franks returned to Toronto with a new urgency. The suit had proven itself in flight. Now it needed to be refined, optimized, made ready for the brutal realities of combat operations. He expanded his team, bringing in chemists from the University of Toronto to work on antifreeze solutions, and engineers from the National Research Council to improve the valve and pump mechanisms. The Banting Institute laboratory became a round-the-clock operation, with seamstresses working in shifts, test subjects cycling through the centrifuge, and Franks himself sleeping on a cot in his office most nights. By March, they had developed a glycol water mixture that remained liquid at temperatures down to minus 30 degrees Celsius without degrading the rubber bladders. The new formula was tested extensively on the centrifuge, then in a cold chamber borrowed from a refrigeration company, then finally in flight at RCF Station Trenton during a particularly bitter cold snap. The suits performed flawlessly. Production accelerated. By the end of March 1941, the first batch of operational suits was ready for shipment overseas, but where to send them? The RCAF had squadrons operating in Britain, North Africa, and across Canada in training roles. The suits would have the greatest impact where the combat was fiercest, where pilots were pushing their aircraft to the absolute limits. Wing Commander Curtis made the decision. The first shipment would go to No. 401 Squadron, a Canadian fighter unit operating Spitfires out of RAF Biggin Hill, the same airfield where Flight Lieutenant James McLeod had blacked out during the Battle of Britain 4 months earlier. If the suits could prove themselves there in the crucible of aerial combat over southern England, they would prove themselves anywhere. April 1941, RAF Biggin Hill, Kent, England. The suits arrived in wooden crates marked with red stenciled letters, indicating military priority. Squadron leader Ernest McNabb, commanding officer of 401 Squadron, opened the first crate with a pry bar, pulled out one of the strange rubber garments, and held it up to the light. He had received a technical briefing from RCF headquarters, read the test reports, understood the theory. He was also a pragmatist who had seen dozens of supposed wonder weapons fail to live up to their promises. His pilots were exhausted, flying multiple sorties per day, escorting bombers deep into occupied Europe and tangling with Luftwaffe fighters that were getting better, faster, and more aggressive. They did not need distractions. They needed advantages. McNabb selected 6 pilots to trial the suits, experienced men who had the skill to evaluate the equipment honestly. Among them was Flight Lieutenant McLeod, who had returned to active duty after his blackout incident in September. McLeod had been grounded for 2 months while medical officers tried to determine why he had lost consciousness during a routine turn. They found nothing physically wrong with him. His heart was strong, his reflexes sharp, his vision perfect. The problem was not his body, it was physics. He had simply pushed too hard, pulled too tight a turn, and his circulatory system had failed to keep pace. The doctors cleared him to fly again, but warned him to be more conservative with his maneuvering. McLeod had smiled politely and said nothing. In air combat, conservative maneuvering meant death. When McNabb showed him the suit, McLeod examined it with intense interest. He had heard rumors about Canadian research into high-G protection, but seeing the actual device was different. He asked if he could try one immediately. McNabb agreed. They found a suit that fit reasonably well, and McLeod changed into it in the squadron ready room. It was awkward, uncomfortable, and made him look vaguely ridiculous. He did not care. If it worked, if it let him pull the turns he needed without graying out, he would wear it gladly. The next morning, McLeod flew a patrol over the channel wearing the suit. The mission was uneventful, no enemy contact, just 3 hours of cold, monotonous vigilance. But during the return flight, McLeod decided to test the suit properly. He climbed to 15,000 feet, checked that no other aircraft were nearby, and rolled into a steep diving turn, pulling back hard on the stick as airspeed built rapidly. The Spitfire responded instantly, G-forces slamming him back into the seat. 4 Gs, 5, 6. His vision began to narrow, but it held. He pulled harder. 7 Gs. The airframe was groaning, the controls stiffening, but McLeod remained conscious, aware, fully in command of the aircraft. He leveled out, heart pounding, breathing hard, but his mind absolutely clear. He landed at Biggin Hill, taxied to the dispersal area, and climbed out of the cockpit with a grin that his ground crew had not seen in months. When McNabb asked for his assessment, McLeod's response was simple. Every pilot in this squadron needs one of these suits. Every pilot in every squadron. This changes everything. Over the next 2 weeks, all 6 trial pilots reported similar results. The suits allowed them to maneuver more aggressively, sustain higher G-loads, and recover more quickly from extreme maneuvers. In combat, this translated to tangible advantages. They could outturn opponents, evade attacks more effectively, and press home their own attacks with greater confidence. Squadron losses dropped, kill ratios improved. Word spread quickly through the RAF fighter squadrons. The Canadians had something new, something that worked. By June 1941, demand for the suits far exceeded Franks's ability to produce them. The Banting Institute was manufacturing 50 suits per month, but hundreds of pilots wanted them immediately. The British Air Ministry took notice and authorized licensed production at facilities in England. American aviation researchers, observing the results, began their own development programs. The anti-G suit, once dismissed as an impractical laboratory curiosity, was becoming standard equipment. But for Wilbur Franks, standing in his Toronto laboratory in the summer of 1941, watching seamstresses cut patterns and fill bladders with glycol solution, the true measure of success was simpler and more profound. Somewhere over Europe, a pilot was pulling a desperate turn, hauling his aircraft through forces that should have knocked him unconscious. But he stayed aware. He stayed in control. He survived. And he flew home. The suits were saving lives. Nothing else mattered. August 1942. Over the English Channel, 22 feet. Flight Lieutenant James McLeod rolled his Spitfire inverted and pulled through into a split-S maneuver, diving toward a formation of Focke-Wulf 1990s that had just bounced a group of RAF bombers returning from a raid on occupied France. The altimeter unwound rapidly as he plummeted through 15,000 feet, 14, 13, airspeed building past 300 miles per hour. The nearest FW-190 was turning hard left, trying to line up on a struggling Wellington bomber trailing smoke from its port engine. McLeod pulled out of the dive at 8,000 feet, the G-forces crushing him into his seat, but his vision remained clear, his mind focused. 7 Gs, the Franks suit squeezed his legs and abdomen with hydraulic firmness, forcing blood to stay where his brain needed it. He centered the gunsight pipper on the Focke-Wulf's fuselage and pressed the firing button. 8 Browning machine guns hammered for 2 seconds. The German fighter shuddered, rolled right, and began trailing black smoke as it fell away toward the channel below. McLeod pulled up into a climbing turn, scanning for threats. His wingman called clear on the radio. The bombers were limping toward home, the German fighters breaking off and heading back to France. McLeod checked his fuel, confirmed he had enough for the return flight, and formed up with his squadron. Another mission complete. Another day survived. He flexed his legs inside the suit, feeling the reassuring pressure of the water-filled bladders. 18 months ago, a maneuver like that would have left him unconscious, tumbling through the sky, helpless. Now it was routine. Across the Atlantic, in laboratories and engineering facilities throughout North America and Britain, the anti-G suit was evolving from Franks's original design into increasingly sophisticated variants. The Royal Air Force Institute of Aviation Medicine at Farnborough had taken the basic concept and refined it, creating suits with improved materials, better valve systems, and more ergonomic construction. American researchers at the Mayo Clinic, working in parallel with the U.S. Army Air Forces, developed pneumatic versions that used compressed air instead of water, reducing weight and eliminating the freezing problem entirely. The Canadians continued refining the liquid-filled design, incorporating feedback from operational pilots and adjusting the suits to work with different aircraft types and mission profiles. By late 1942, thousands of anti-G suits were in service with Allied air forces. The designs varied, but they all traced their lineage back to the same source, to Wilbur Franks and his mice in the Banting Institute centrifuge. The impact on aerial combat was measurable and significant. Pilot blackout incidents dropped by more than 60% in squadrons equipped with the suits. Aircraft loss rates decreased, combat effectiveness increased. Pilots reported greater confidence in aggressive maneuvering, knowing they had protection against the invisible enemy of G-induced loss of consciousness. The suits also enabled tactical innovations that would have been impossible before. Fighter pilots could sustain tighter turns for longer periods, allowing them to stay with opponents who might otherwise have escaped. They could execute more violent, evasive maneuvers when under attack, throwing their aircraft through the sky with a ferocity that would have incapacitated unprotected pilots. They could recover more quickly from high-G situations, maintaining situational awareness and decision-making capability in the chaotic, split-second environment of air combat. But the suit's influence extended beyond fighter operations. Bomber pilots used them during evasive maneuvers when under attack by flak or fighters. Transport pilots wore them when flying through turbulence or conducting emergency descents. Test pilots used them when evaluating new aircraft designs that pushed performance boundaries. The anti-G suit became, within 2 years of its invention, an essential piece of equipment for anyone operating high-performance aircraft in demanding conditions. Franks himself remained in Toronto throughout the war, directing the Canadian production program and continuing research into physiological protection for aircrew. He was not interested in publicity or recognition. He attended technical conferences when required, published papers in medical journals when time permitted, and spent most of his energy ensuring that the suits being manufactured met the standards necessary to keep pilots safe. He received letters from pilots, dozens of them, some expressing gratitude, others offering suggestions for improvements, a few simply saying that the suit had saved their lives. He read each one carefully, made notes, and incorporated the feedback into ongoing development work. In 1943, the German Luftwaffe began deploying its own anti-G equipment, crude inflatable bladders that provided partial protection but lacked the sophistication of Allied designs. Intelligence reports suggested the Germans had captured a Canadian suit from a downed Spitfire and attempted to reverse engineer it. They succeeded partially, enough to improve their pilots' tolerance, but they never matched the performance of the Franks suit or its derivatives. The Allies maintained an advantage in high-G combat throughout the remainder of the war. As aircraft performance continued to advance, the anti-G suit evolved with it. The jet fighters entering service in the final year of the war generated even higher G-forces than their propeller-driven predecessors. The first-generation Franks suits were adequate but not optimal for jet operations. Engineers redesigned the bladder configurations, increased pressure levels, and developed rapid inflation systems that could respond more quickly to sudden G onset. By 1945, the anti-G suit had become a sophisticated piece of physiological equipment far removed from the hand-sewn rubber prototype Franks had demonstrated at Downsview in 1940. The war ended in August 1945. Millions of soldiers, sailors, and airmen returned home. The vast industrial and scientific apparatus that had been mobilized for war began the slow process of demobilization. But some technologies, some innovations proved too valuable to abandon. The anti-G suit was one of them. Military aviation continued to advance in the post-war years, with aircraft becoming faster, more maneuverable, and more capable of generating forces that challenged human physiology. The anti-G suit remained essential equipment, continuously refined and improved as new materials and engineering techniques became available. Wilbur Franks returned to civilian medical research after the war, working on cardiovascular physiology and continuing to consult with the RCAF on aerospace medicine issues. He published extensively, trained a generation of researchers, and received numerous awards and honors for his contributions to aviation safety. In 1952, he was made an Officer of the Order of the British Empire. In 1986, he was inducted into Canada's Aviation Hall of Fame. He accepted these recognitions with characteristic modesty, always emphasizing that the suit was the product of collaborative effort, that many people had contributed to its development and refinement. He was correct, of course. The anti-G suit that entered widespread service was not the work of one man alone. It was the product of seamstresses and engineers, test pilots and medical officers, chemists and physiologists, all working toward a common goal. But it was Franks who saw the possibility when others saw only limitations. It was Franks who believed the human body could be protected, could be given the tools to match the machine's capabilities. It was Franks who refused to accept that pilots would simply have to live with the constant threat of blacking out in combat. The numbers tell part of the story. Estimates suggest that anti-G suits prevented thousands of blackout incidents during the Second World War, incidents that would have resulted in aircraft losses, pilot deaths, or mission failures. The suits allowed Allied pilots to fight more effectively, to survive situations that would have been fatal without protection, to push their aircraft and themselves to limits that redefined what was possible in aerial combat. But numbers, however impressive, cannot fully capture the human dimension of what Franks achieved. There is Flight Lieutenant James McLeod, who flew 112 combat missions between 1940 and 1945, survived the war, and returned to Canada to become a commercial airline pilot. He flew for another 30 years, retired in 1975, and lived to the age of 83. He attributed his survival during the war, in part, to the anti-G suit that let him maneuver aggressively without fear of losing consciousness. There are hundreds of pilots with similar stories, men who came home because they could stay aware, stay in control, stay alive in situations where physics should have killed them. The anti-G suit also changed how engineers designed aircraft. Knowing that pilots had protection against high G forces, designers could create aircraft capable of more extreme maneuvers, tighter turn rates, higher acceleration profiles. The jet fighters of the 1950s and beyond were designed with the assumption that pilots would be wearing G protection, that they could withstand forces that would have been lethal a generation earlier. The suit and the aircraft evolved together, each enabling the other, pushing the boundaries of what was technically possible and operationally practical. Modern fighter pilots wear G suits as a matter of routine. The current designs bear little resemblance to Franks's original water-filled prototype. They use sophisticated pneumatic systems, computer-controlled inflation, and advanced materials that provide protection up to 9 Gs or more. They integrate with flight suits, oxygen systems, and survival equipment. They are lighter, more comfortable, and more effective than anything Franks could have imagined in 1940. But the fundamental principle remains unchanged. Surround the lower body with pressure. Resist the pooling of blood. Keep the brain supplied with oxygen. Stay conscious. Stay alive. In 1986, a young Canadian fighter pilot named Julie Thériault became one of the first women to fly the CF-18 Hornet, a modern multi-role fighter capable of sustained 9G maneuvers. She wore a G-suit designed to protect her during the extreme forces generated in air combat training. The technology had advanced enormously since Franks's era, but the lineage was direct and unbroken. She was flying because Franks had refused to accept limitations, because he had believed that human physiology could be protected and enhanced, because he had spent years refining a strange rubber suit that almost no one initially believed would work. Wilbur Franks died in 1986 at the age of 85. His obituaries noted his contributions to aviation medicine, his wartime service, his post-war research. They mentioned the anti-G suit, the thousands of lives it saved, the way it transformed aerial combat and enabled the development of modern high-performance aircraft. But perhaps the most fitting tribute came from a retired RAF pilot who wrote a letter to a Toronto newspaper after Franks's death. The letter was brief, just 3 sentences. Dr. Franks gave me the ability to survive maneuvers that should have killed me. His suit kept me conscious when physics tried to shut me down. I owe him my life, and I never got the chance to thank him properly. The letter was signed by dozens of other pilots, Canadians and British and Americans and others, men who had flown in the war and afterward, men who understood that they had lived because a Canadian doctor had refused to accept the limitations of the human body and had found a way to push beyond them. The story of the anti-G suit is not a story of sudden inspiration or lone genius. It is a story of methodical research, careful engineering, collaborative development, and relentless refinement. It is a story of recognizing a problem, understanding its fundamental causes, and developing a solution that was elegant in its simplicity and profound in its impact. It is a story of Canadian innovation making a difference at a critical moment in history, of science serving humanity, of one person's determination to save lives changing the course of warfare and the future of aviation. The suit itself, the physical object that Franks created, was made of rubber and water and valves, but what it represented was something far more significant. It represented the refusal to accept unnecessary death. It represented the belief that human limitations could be overcome through ingenuity and effort. It represented the idea that technology should serve people, should protect them, should give them the ability to do things that would otherwise be impossible. Somewhere in the skies above us right now, a pilot is pulling a high G-turn, the forces crushing their body, their vision narrowing at the edges. But they do not black out. They do not lose control. They remain conscious, aware, capable. The G-suit wrapped around their legs and abdomen is doing its job quietly, invisibly, keeping blood flowing to the brain, maintaining awareness, preserving life. The pilot does not think about the technology protecting them. They are focused on the mission, on the aircraft, on the immediate demands of flight. But the protection is there nonetheless. The legacy of Wilbur Franks and the impossible suit that let pilots survive forces that should have killed them. It is still saving lives 8 decades later, and it will continue saving lives as long as humans push against the boundaries of what is possible, as long as we build machines that challenge our physiology, as long as we reach for the sky and refuse to let our limitations define us.